Okay, thank you very much. So let's continue for today's lecture. We are now in lecture 6, which is the second part of multi-cycle RISC-V. So the goal for today really is about learning how to design the finite state machine controller. Because last week, um, you should have noticed that for every cycle that we run our code, our multi-cycle processor in, the control signals are different for every cycle. That entails that we have to make sure that our controller, right, the controller needs to be clock dependent because it depends on what cycle. The control signals depend on specific cycles. So a recap from last week, right? So the trick really is to design the controller to use a finite state machine. Now, hopefully, you will remember what finite state machines are from 111 or even CoE 23 or triple 11. And for some, for triple E 143 and so on. We'll also review it a bit later. But somehow, I expect that since the prerequisite of this course is that you've gone through the basics of digital circuits, somehow finite state machines was you should be able to recall a bit more about finite state machines. Now, recall that our operations last time they vary between 3 to 5 cycles. It's load words are usually 5 cycles long. Star words 4. Register types or actually any data processing instructions are also 4 cycles long, and then branching are just 3, right? And depends whether you have branch taken or not taken. Now, our goal is that for every cycle, we want to deliver these signals properly to the system. Okay. Now, it's very easy to do because last week when we made our tables, this thing, right, this cycle control signal table, it's so easy to write down the state machine, or actually it's possible that you can jump right ahead and code your finite state machine controller in Verilog already. So today we'll try to understand, or I will demonstrate to you guys how to plan out, how to make that state diagram using these tables, right? So we need to make some assumptions. I'll jump ahead because sometimes there are two ways to design your work. You can do bottom up or top to bottom. So I prefer, although yeah, for me, I prefer the top to bottom. That sometimes you usually try to draw the bigger picture first, and then you build things part by part, rather than tackling the small parts first, and then all at once. You just trust that you're making the small pieces good for the bigger picture, right? So for here, we'll make a few assumptions that the controller uses a more finite state machine. We'll get back to that. But what it basically means is that the output changes only with respect to the state. So any change in the input doesn't change the output, but only changing the state does change the output. So by our main controller, I mean this main finite state machine that controls this specific set of signals, right? Now ALU control, the one that you feed into the ALU, whether if it's an add, an or something, it's more of a mealy output, okay? Because it's dependent on the state of the finite state machine, and at the same time, it's also dependent on a set of inputs, right? So that's what the ALU control would be. Now, the PC write as well, over here, as you can see, it's dependent on the zero signal that comes from the ALU. So it's also a quote-unquote a mealy. Well, really, it's a mealy because it's also dependent on the current state of the finite state machine. The IM source down here is from the instruction decoder is fully combinational, right? Now, this slide is not so important, but maybe later on when you're trying to restudy the slides or look into or review this video lecture again, the thing is that these minute details would be very much implied in the state machine that we're working on later. Okay. So yeah, so right now maybe it's not so important, but maybe later on when you start to go back and try to draw your own finite state machine, yeah, you'll come to realize, so that's how it works. Okay. So for now, I just mention it here for the completion of the discussion. All right. So let's design the longest instruction first, which is the load. And when you make a state machine, the first thing that you have to make is a state diagram, right? Well, if you're a professional digital designer already, that you can just draw things right off the bat from a single table, that's totally fine. But at least for me, uh, I really prefer to draw state diagrams for documentation purposes because it's easy for people to understand. Okay. So let's start with the load instruction. So we go through cycle per cycle again. So the first stage, if you remember last time, is the fetch and the PC update. Right. So I've highlighted in red all the fetch components or the paths of the fetch that are needed. So you're essentially just loading the PC into the memory, right? And then the memory loads the corresponding instruction for that program counter into the instruction register, right? And then, of course, the PC update is in this green path. As mentioned last time, it's during the fetch cycle, cycle 1, where we do both a fetch and a PC update. So that in the next cycle, this PC register is updated immediately. Okay? And don't forget, these things in green here are highlighted to be the control signals important at this moment. Okay, and remember, I mentioned earlier that we're gonna do a Moore finite state machine, such that the outputs are dependent on the state. So cycle 1 would be essentially state 1. And the only thing you have to think about is that, okay, in cycle 1 or in state 1, what are the control signals that I need? Right. So we've listed it down here already, totally fine. Right. And because we know that these control signals are important, that's the things that we are going to put in our state machine. Now, if you're wondering, what about the memwrite, IM source, and the readwrite? Well, you have to put them down as well. Okay. But let's make the assumption that if it's not written in the state diagram, all other outputs are mostly zeros rather. Okay. The IM sources I don't care because we don't need it right now. It literally can be any value because it's not needed for the stage. But sometimes people don't care. People prefer to put the last state or 00 to be the default. I prefer to put it at 0 for the sake of clarity that hey, I'm not using it, or usually 0 means empty or not being used anyway. Okay. So going back, um, grab all the important signals, right? Grab all the important signals, take note of their states, and then put it as the first state in your state diagram, right? So upon reset, when you start your processor and then you do the reset, all of these control signals all of these green signals are there. Okay, so that's pretty much it. So you can compare them side by side later on. Okay, so put it there. Set state 0. These are the important signals that I need to do. I need to set. Okay, and then upon reset, the first step is to always fetch and take note if it's not stated, assume all other signals are 0. So the things like the memory write or the memory write, the register write, the IM source, let's just assume there's 0 as of the moment. Okay. So it's easier. You can optimize it later on, but the point is that just write down the important signals that you need. Okay. So this is the first fetch state. So the second cycle is to decode. As you notice here, I did not put any highlights. Why? Because if you remember last time during the decode state, the job of the multi-cycle processor is just to literally just hold the value here and then use that cycle just to load the data from the register file into the register over here, the IRF, right? The IR. Right? So the intermediate register rather. Okay. So because basically the thing that the code does is just, hey, I'm going to use this cycle just to understand and interpret what your control signals are, because this is where the instruction is held, right? And of course, it also goes into the control unit. So when you're in the control unit, it starts to interpret, hey, what do I have to do given this set of instructions? Okay, that's pretty much it. So don't do anything. As you can see here, I didn't highlight anything because there's nothing really important. So as mentioned earlier, if you put it here in the state, so that's the next state, it does nothing because you just need it for the decoding state. So since there's nothing in it, assume all other signals are 0. Actually, the important signals that need to be zeros are those write enable signals. By write enable signals like PC write, mem write, IR write, read write, those need to be 0, right? And all the rest look. So don't care, and even much more don't cares. So they can be any value or 0. It's a don't care, right? So yeah, don't do anything. State 1, decode. That's it. The next state of the load word, if you remember last time, is the execute stage, right? So during the execute stage, what do? We calculate the target address over here. And then again, just highlight which signals or which control signals are important. You have the ALU source A, the ALU control, ALU source B, and then the immediate extension. Okay, so just highlight, grab those things, put it in the state diagram. Bam, that's it, right? So going back here, just to make sure we understand, ALU control needs to be 000 because we're adding the register X2 with the offset 143, which is going through this path, right? ALU source A needs to be 10. Yep, 10, not a problem. ALU source B needs to be 01 because it's grabbing the extension. So 01. And then the immediate source needs to be 00 because we're doing a normal immediate, right? So either immediate instructions and load word, you're using the normal immediate format for the immediate extension. Okay, so that's pretty much it. So the story sort of goes over and over again. So grab those important signals, put it into the next state, and then flap there. Just that, that's just the only thing you have to watch out for. And then make sure all other signals are zeros or don't cares. Just make sure you're consistent with the signals. Okay. So here's the other thing. Because we know it's a load word instruction, you have to make sure that this state only changes to the memory address state, okay, or the memory access state. Because when it is a load word instruction, and you can determine if it's a load word instruction depending on the opcode, right? The opcode funct or funct3, funct7, but in this case, we only need the load word because you can immediately tell, hey, what do we need? Okay. So what about this fetch state to decode state? Well, there's no input that changes from fetch to decode. It's like immediately in the next cycle, you have after the fetch, you have to move to the decode. So you don't specify the condition that it needs to move to the decode state. But for the decode state, actually, this will branch out later on, okay, as you'll see. You have to from the decode state, if you're doing a load word and it has a specific set of control signals, you have to make sure you specify, hey, what makes me move from the code state to the memory address state, okay, or memory access state. I just put memory address because technically we're computing the memory address during the execute state at this point, right? So yeah, just make sure you take note of that. So in the next state is really the memory access, wherein we're gonna obtain from the memory. All right. So remember earlier in execute state, we calculated the target address. It will be saved in the ALUR, right? The ALU register, which is the ALU out, which contains the target address as well. Then you have to feed it back into the memory right over here. Okay, because we need to load the next cycle, right? We have to grab the data that we need, and then we're going to load it into the DMR, the data memory register down here. Okay, and then take note, what are the control signals again that you need? Just the ADR, address source, right? And the result source, because you need to grab whether if it's from the ALU out or somewhere else. Okay, so again, grab those two, put it in the next state. So we put that into the memory read state, but you also have to specify it's from the load word. So I'm getting ahead of myself over here, but you'll see that it changes depending on the operation that you're using. Okay. Okay. So that's the third state. Finally, the last state for the load word is the write back, which is to, hey, the data is already available in my DMR. That's the data that we grabbed from the memory. And then all we have to do is to write that back into the register file, right? So again, what are the two control signals? The write reg down here, and then the result source, which swaps immediately in the next stage. Grab those two, put it in the state machine, and we know that this is the last cycle for the load word. So if you look at the state machine, bam, you're there already. So you just have the right memory write back stage, feed it back into the fetch stage again, because in the next cycle, you start from quote unquote cycle one, or the fetch state, fetch stage or fetch state. Okay. So it's pretty much simple. I think by this moment you're supposed to somehow grasp already. Hey, how are we gonna do this state diagram that we need? Okay, so it's pretty much simple, right? And the very highlight or the very useful method here is the use of the table that we made last week. Okay, use the table, highlight the important signals, assume all other signals that are not important as zeros or don't cares. Okay, and then you can just eventually make the entire state diagram. Okay. So let's try the next instruction. Let's try this store word instruction. Pretty much the same thing, but take note it only takes 4 cycles. And we'll see how we can actually incorporate that into our state diagram. Now note that the fetch, decode, and execute stage for the store word is pretty much the same for both load word and store word. Okay. So we'll go through that very quickly, but I won't highlight the signals anymore because I mentioned that they are the same. But if you remember, the fetch stage, actually the fetch stage is always almost the same for everything, right? Fetch stage, so you can just reuse the same state earlier. The decode stage, don't do anything, but I'd like to highlight that we're also grabbing RD, but hey, it's part of the system already. That you don't have any control signals to control the loading of the destination register, right? It's just fixed here when you loaded it into the intermediate register, right? So decode stage is pretty much the same. Execute stage is also the same because you do this register plus immediate operation. Okay? So when you look into your state diagram, you don't change anything. For the store word, state 1, 2, and 0, 1, and 2, this one, and this one, they're pretty much the same. But the highlight here is that, hey, I also include store word as part of my inputs. Okay? Because, hey, I need it for my memory address too. Okay? So, yeah, that's pretty much it. The first 3 states are the same. Don't do anything. All right? So what about the fourth stage, right? Because the fourth stage is already the last stage, which means we're gonna do a memory write. And again, the same thing happens. Look at your table. Identify the important control signals. We have the PC write, the ALU out, and actually the memory write. Where did I put that? It's this guy over here. Right. So the memory write needs to be a 1. Why? Because when the memory write is a 1, it's an enable signal wherein you can overwrite a specific memory address. Right. So have those 3 over here. These 3 signals that are important. So it's actually address source and what do you call this? Result source is pretty much the same actually for load word and store word, but you have to add this additional memory write that needs to be there as well. So even though we have just one signal that's different from the load word, we have to make sure that it belongs to a different state because again we're using a Moore state machine such that the outputs are dependent on the state. Okay. So again, grab the signals, grab everything, and then clap, put it up there. And because memory, or sorry, the store word is fourth cycle is the last stage, you put that feedback into the fetch stage again at the very beginning. Okay, so that's pretty much it. So this is the state diagram already for the store word, and the only thing that we had to add was this extra state where you do the memory writes. Okay, and it branches away from the operation of the load word, right? So if you do a load word, make sure it goes to the memory read. If you do a store word, it goes to the memory write. Okay, so that's pretty much it. So next is the R type or the R type instructions. So if it works for the AND, it will probably work for all the others as well. So recall it only takes 4 cycles and note that fetch and decode states are the same. But the execute stage is different because we're not using an immediate anymore. We're using register to register operations. So again, cycle and repeat, fetch, no change, decode, no change, but highlighting that we only need the 2 register sources, but we don't need to do anything still. So both fetch and decode are recycled, don't have to change anything, not a problem. But when you get into the execute stage, we now start grabbing whatever is in the destination register. Or no, the read data registers rather. Okay. So again, get the control signals that are important. We just need 3. The ALU control, however, as you'll note, is that it's for an AND, so it's 0, 1, 0. But at the back of your mind, which is the minute detail I mentioned earlier, that the ALU control actually depends on both the state and the opcodes that you're using. Actually, these 3, right? Because that's the one that's controlling ALU control. Okay. Whatever is the opcode is and the func signals are, they're the ones that indicate that, hey, are we going to do an add, a subtract, an and, an or whichever of those, right? So it's actually a mealy state output because it's dependent on both the state and a function the of these control signals from the instruction. But not to worry about, the ALU source and B are pretty much the same. So grab these things and put it into the uh, state diagram. There, right? So you have the execute reg, and it only works when you get into the when your opcode is pertaining to R-type instructions, right? Now you'll notice here that the ALU control is a function of opcode func3 and func7. Totally fine, okay? Because that indicates that, hey, my outputs for ALU control are mealy because I'm not just dependent on the state, but I'm also dependent on control signals that are important for that ALU control signal. Okay. Now here's the thing, and this is for cycle 3. In cycle 4, we also have a write back state, but it's different. So what makes it different is that you're grabbing the result immediately from ALU out, not from the memory DMR here, right? Because in the next, from cycle 3 to cycle 4, you're loading the result in the ALUR, okay? And then from that ALUR, you're gonna have to feed it back into the register file. And what are the two control signals that you need? Result source needs to be 0, 0, and the reg write needs to be 1. So it's a separate state in your state diagram. Then you'll have it right here. There, right? And of course, we know that cycle 4 is the last state. You feed it back to the fetch, and then you're done. Right? So that's how quickly you can do it. All right, we're actually going at a pretty good pace. Okay, stitching the state machine for the I-type instructions. So add I, pretty much the same thing. We didn't discuss this last time, but I assume, or it would be a nice exercise for you rather. So what do you need for the add I instruction? All right, so we'll go through it again. We'll go through it very quickly here, but I'll go through it like a breeze because it's important that we're just gonna stitch the state machine. Okay. The only difference really now is that you have to set the immediate source from in the ALU source B. But again, you should notice that the fetch and the decode states are quite repetitive right now. And because of that, let's jump to stage 3 immediately, okay, for the execute stage. Bam! All right. So in the stage 3 and the execute stage, you still need the important control signals. Pretty much, actually, at this point, it looks like the, what do you call this? It looks like the load word instruction. But the only thing that you have to notice is that the ALU control is actually function dependent. Okay, it's dependent on the control signals here. All right. So it does look like the register instruction, but at the same time, you have to reroute the source B to grab the immediate extension down here, right? So grab all these four, and then and take note that the immediate source needs to be 0, 0 because it's a normal immediate. Okay, and then if you put that into state diagram, bam, you'll have it the same thing. Okay, so ALU control is function dependent. It's a mealy. The IM source is now there. Unlike it's not here. It's not no, well, it's here, but in the execute stage of the register, it's not there. Right. So it's pretty much the same thing. They almost look alike except for the ALU source B and the IM source. But then in the next cycle, right, when we write back, it uses the same write back state of the register, right? So if you're gonna go back a bit, the write back state of the register is really, you know, if you put it into the immediate instruction, it's loaded here, and you're just gonna have to write back like a normal register, right? So that's why at this point, immediately after execute of the immediate instruction, you write back immediately. You go to the same ALU write back, right? But take note, you branch from this point, from after the decode, you start to branch into a separate immediate state because you're able to detect that, hey, from the opcode, I'm doing an immediate instruction. Okay, so that's the write back stage immediately, and then go back to the fetch stage, and then you're done. You already have the state machine, or rather the state diagram for that supports immediate instructions. So we have a lot already. We have load word, store word, register, and then immediate instructions. We have one more thing, branching, right? So we'll try to do branching. Now this thing has a special part because if you noticed earlier, we'll go back again, there's nothing in the decode stage. But from the discussion last time, which we'll go through again very quickly in a bit, during the decode stage, we can actually branch instructions immediately. Or sorry, we can actually compute during the decode stage the target address for branch instructions, right? So that's a special part in the decode stage. all right? Because we can compute the target address immediately. So we're gonna go fetch first. Nothing changes in the fetch. Okay, but during the code, here's the highlight of it. Last time or in the previous instructions, during the code stage, there are no operations being handled at that moment. But here, because during the decode stage that the ALU is not being used, we did say last meeting that for branching instruction, we can calculate the target address at this point. So we can calculate that by just, hey, these are the control signals that I need, right? So the AL control, AL source, source A, source B. Of course, the IM source needs to be 10 because it's doing the store type immediate format. AL source A needs to grab the old PC, and then AL source B needs to grab that immediate because and then ALU source, or sorry, the ALU control needs to be an add, so it's 000 because the result here is the target address. Okay, if the branch will be taken. And we know immediately in the next cycle during the execute stage, the ALUR here, will be holding the target address. Okay, so that's something you have to watch out for. So, hey, since the ALU is available during the decode stage, why don't we always compute the next target address, right? Assuming we're gonna do a branching. Okay? It doesn't matter really if you're doing other instructions, right? The point is that we're trying to pre-compute something ahead. So regardless of branching, yes, it is regardless of branching, and I'll explain in the next slide. Okay. So you're gonna grab these signals, okay, put it in the decode stage and put it there all the time, right? And yes, it's regardless of branching, because whether you do load word, store word, or register or immediate type instructions, it doesn't care about the ALUR result, because in these cycles, we're going to overwrite the ALUR register, right? So hold on, I'll use it here again. Erase a bit so that it's clear. Pen. So, okay, I'm gonna go back and forth between slide 36 and 37. Okay, so here, if it's branching, we're gonna compute it. If it's not branching, we still compute it. Okay, because it's like trying to look ahead. Hey, just in case we're doing a branch instruction, let's compute it. But during the fetch stage, we don't know yet, right? Or rather, during the decode stage, well, yes, you could argue that you can immediately do a branch already, but we want to save up on states, because if you try to branch these with whether you have a VQ state over here, is we're technically wasting another state for our controller, right? So we have this clever idea, since ALU is not being used, right? Why don't you just put it in the decode stage? And then in the event that you're gonna do a load word or register an immediate type, it doesn't matter. If you compute it in the decode stage, right, and then it computes some target address here, even if it's some dubious or erroneous data that doesn't make sense. In the previous stages for the other instructions, we don't care about it, right? Because we're gonna compute a new target address or a new data to be loaded into the ALUR. Because at that state, like for the example, I'm gonna go back a bit, right? Like the add I state over here, right? In the execute state, that you would say that the target address, quote unquote target address during the decode is already here in the ALUR, but our add I or add instructions are not needed. Does not need that ALUR, right? Because eventually, ultimately, you're gonna compute a new target result, which is gonna be loaded here. So it's safe to say that, hey, in my decode stage, if I put my branching instructions there, it doesn't matter for all other instructions, all right? Because you don't need it. But we do need it for branching instructions, okay? We do need it for branching instructions. And rather than having a separate state for the branching instructions, let's just put it in here anyway. It doesn't matter, okay? Because even if you have a separate state for branching instruction, it's just an extra state in the first place. No, you don't want to do that, okay? You'd rather reuse your current system for other purposes, even though it's not going to be used in the next cycle. At least now we're safe to say that, hey, I can reuse this state. I hope that answers your question. Does it make sense? Okay, very good. Fantastic. It makes sense. Okay, right. So the point is we can reuse that state over here. Okay, we can reuse the decode state to compute the target address in advance. right? And regardless if you're using any other states here, 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 or here, doesn't matter because we don't need it. We're just using the state to compute it ahead of time. All right. So that's actually a good question, but yeah, quick answer, yes, regardless of any instruction, right? So in cycle 3, we have two states, right? We have, or rather, two cases. The branch is taken and the branch is not taken. Now in cycle 3, right, we have during the execute stage, what we do in the execute stage is that we've loaded the data into our register IRF over here, right? The intermediate register file register. Okay. And then what we want to do is that we want to compare the values, right? If it's a branch of equal to, what you do is that you grab that data there, you grab that data here, ALU control, source A, source B, but the ALU control needs to be a subtraction. Okay, so take note of that. We need to subtract because we want to determine if it's a 0 or not. If the result is a 0, right, and we know that we're doing a branch instruction, and we know that we we know that we're gonna do a branch instruction. The thing is that okay, if that's gonna happen, then we can determine if we take the branch or not. If the result is 0, the entire ALU result is 0, and the 0 is asserted, we do the branch instruction, right? And then that PC right over here is asserted. Okay, this thing over here as well as the ALU source over here. And take note, the ALUR over here is holding the target address already. It's equal to the target address, which we computed in the decode stage, just in the previous stage, right? So it is already readily available here. And if we are happy that the branch will be taken, the ALU understands that, hey, we have a 0 signal. Okay, the controller unit says, oh, the 0 signal is there, and we're doing a branch instruction. Okay, then we take the ALU result. We wrap the ALU result back into the program counter. We set the PC right to overwrite the program counter into the next branching address. Okay, so grab these signals again and put it in the state diagram. Okay, now take note though that the tricky part here is that, hey, this is when the branch is taken. What about the scenario when the branch is not taken? Well, the only thing that changes really, I'm gonna erase the figure, erase all ink on the slide. Yep, the only thing that differs really when it's not taken is that, and I'd like you to take note of this feedback part here, is that if the branch is not taken, then we're just not using the branch at all, right? We're not using the ALU result. We leave it there. Okay, so we make sure to set PC right to 0 so that we don't update it over here. And then the ALU, the result source can be a don't care, or just, we can still feed it back, not a problem. If you set it as 0, 0, not a problem. Because even though you feed it back here as 0, 0, but then the PC right is 0 anyway, we're not updating the program counter. So when the branch is not taken because the 0 signal is not asserted, it's 0, right? Then we just don't use the feedback path again anymore. Okay, we make it completely useless, right? So there are two things that are important here. One is that the ALU control source A and source B. If you compare it with the branch not taken, you can look at that 001, 1000, and the branch taken, right? They're pretty much the same. So these are state dependent. But the result source, you have here the 0, 0, and the PC right now and 1. And if you go to the branch not taken, right? Actually, I should have pointed it out here instead. This one are mealy dependent because they're dependent both on the result of the 0, okay, and the state that you're at, right? And because of that, PC write and result source are mealy dependent. The way you're gonna write it in the state machine would be something like this. All right. Actually, the result source can be 0, 0. Doesn't matter anyway. Okay. So A, source control. You could argue that the result source is 0, 0. Okay, because if you go back here, whether you are 0, 0 or don't care, why not just set it as 0, 0 anyway, right? I don't care whether the branch is taken or not. But the important part here is that the PC write is dependent on the branch signal. Whatever you have in the control finite state machine, and then you say, hey, I have to make it as a branch dependent, then a PC write is a MIDI output that's dependent on the branch signal. Okay. And then when you're done, you just feed it back to the fetch signal. And that's it. That's the entire state machine. right? This is your full state machine already, or rather full state diagram. Actually, I should put that as diagram rather than state machine. But the goal is to make a state machine later on because that's what you're gonna write into the system. Question. Sir, where would the PC plus 4 come from for not taken? Okay, that's a very good question. Okay. Where would the PC plus 4 come from if it's not taken? Okay. Um, we will have to go back to the cycle 1. Okay. Remember, in cycle 1, right? In cycle 1, when we do the fetch, right? When we do, okay, so put it this way. In cycle 1, we're looking at the current PC. So the PC here is, say, how do I put it? Let's say the current PC is PC, okay, in cycle 1. But in the next cycle, when you go to the decode stage, right, the current PC is PC, and then the one that you load into the instruction is the instruction for PC, right? So let me rewrite that. So the current PC that you have is PC, and then the current instruction that you have is pointing to PC. Or rather, the one that will be loaded in the next cycle will be PC, instruction PC, right? But since we're doing a PC update at the same time, when you go to cycle 2, I'm going to erase other things here. When you go to cycle 2, your instruction here is still using instruction PC because in cycle 1, that's the only time you update this, right? That's the only time you update that. So in cycle 2, instruction PC is PC, right? But take note at the same time when you do the PC update, right? This one, this in this next cycle, it's going to load the PC plus 4. Okay. So when it loads the PC in the next cycle, when you go to the decode stage, this PC here is actually PC plus 4 already. The one that you're gonna use when you go back to the next fetch stage. Right. So you see here, that's a very good question, right? So PC plus 4 is already loaded in the second cycle, right? But the instruction that we're processing is the one in PC. So when you go to cycle 3, right, the current PC that it's holding is actually PC plus 4, right? So if you go to, let's go to the branch not taken. The current PC that it's actually holding is PC plus 4, right? And since we're not updating PC right during the branch is not taken, this one is 0, right? That thing there, that PC is still holding the PC plus 4. Okay. So when you go into the next state, I don't have the figure, but the point is that when you go back to cycle 1, go back to the fetch state. Okay. So you could imagine that we're going to the back to the fetch state. That PC plus 4 is now already loaded in here. And then when you go to the decode fetch state, the PC plus 4 is overloaded on here, right? And if you go into the cycle 1 again and you're going to fetch, essentially in the next cycle, you're going to fetch the instruction with PC plus 4 already. Okay? Did that make sense? Ang daming nangyayari. But did that make sense or you want me to repeat it? Basically, oh yeah, right. Whoever thought of it was a genius, right? That hey, in the fetch state, let's do the fetch and then the PC update at the same time, right? So since we're not really updating my PC, but my PC plus 4 is already ready. So the next time you go to cycle 1 or the fetch and update stage again, you're actually looking at the PC plus 4 already. So yes, whoever thought of it is a genius. All right. So yes, I'm glad that you understand. Yeah. So when the branch is not taken, since you're not update. The quick answer to your question is that when the branch is not taken, since we're not updating the PC next to the computed target address over here, it's gonna use the previously computed PC plus 4 back from stage 1. Okay. So it's so cool. All right. So yeah, good question. Quick answer. Time check. Yes. Okay. So that's what you have for the entire finite state diagram. Now here's the thing. If you have the finite state diagram, you can code this already into your system. Okay. Now I won't be demonstrating to you in the next slides. We probably next 5 to 10 minutes to discuss a very important topic about finite state machines, right? So for here, we're not, we don't need to. I'm not going to demonstrate rather how to code this thing, but I'm going to demonstrate to you rather how do we actually code state machines in Verilog. Okay. But the important lesson so far up to this point is that hey, these are the steps that we needed to make my state diagram. And if you have a state diagram, it's so easy to code my state machine later on. But let's use a very simple example because it's gonna take us probably an extra hour if you're gonna discuss the entire thing for this. Okay. So how to design a finite state machine? You have to know that the outputs differ if they are milli or more. Right. So this is a bit of a review of your previous classes. So you have a Moore machine, and the diagrams that you down here are the visualizations of how you're gonna think about them, right? So again, Moore machines are machines where or state machines where the outputs are just dependent on the state. Okay, so you have inputs here that can go into some combinational logic that determines the next state, right? And then the state here is the current state, which you feed back into the combinational logic that determines, hey, if this is my current state, and then I have an input that tells you to change into the next state, right? So that's the one that loads the next state. Okay. For this should be milli machines. Okay. For milli machines, the outputs are dependent both on the current state and the input, right? So you have a separate combinational logic that takes an input and the current state, and then you present some out. But the next state logic is pretty much the Moore state as well, rather the Moore-like machine that you have an input and then the current state, and then you combine the two to process it to determine the next state. Okay, so every time when you make a milli or Moore machine, because maybe sometime down your career, if you do digital design, sometimes you have to decide, what do I want to do? Do I want to make it a Moore machine? Do I want to make it a milli machine? Right? These are the two diagrams or the two visualizations that you have to think about. Okay, and it's so much easier to visualize them this way, which I'll demonstrate in the next few slides. Okay, so let's say I want to make a very simple milli machine. Okay, I'm gonna make a milli machine instead because it's very easy to do a Moore machine. Technically, the Moore machine is like a quote unquote a subset of the milli machine. If you grab this thing and then tie this output to the output immediately, that's your out. That's your how would you put it? The that's your Moore machine, which is like quote unquote a subset of milli machines. Okay, so let's consider one very simple milli machine. And if you remember from last time, these circles there indicate the current state. So 0 here is the current state, right? And then we put signals like this. So the left side of the slash is the input, and the right side of the slash is the output. So what this says is that, okay, if I have an input 1, okay, my output should be 0, and I should move to state machine 1, okay, or state 1 rather. This is the state machine, okay. So if I'm in state 0, and I have an input 1, right, my output should be 1, and I have to move to state 1. If I'm at state 0, and my input is 0, my output should be 1 instead, and then I have to move to state 2. Okay. And the same thing goes for the others. If I am at state 1, my input is 1, then my output has to be 0, but I have to go back to state 1. If I'm at state 1, my input is 0, my output still has to be 0, but I have to go to state 2. Right? So it's so easy to visualize the things that are happening with a simple state diagram. Okay. Now, how do you code this? That's the question. Since we're using a milli machine, then always visualize this thing. Oh, and I'd like to re-emphasize again that when you're doing digital design, you are doing hardware description languages. Verilog, System Verilog, they are hardware description languages. They are not software descriptions, or rather, they're not software codes. Okay? They are hardware codes, quote unquote hardware codes. So every time you think about this, right? If I have a milli machine, I'd like to visualize that, or I'd like you guys to think about that. Hey, this is something that we're trying to make. And if you can compartmentalize the output logic, the next state logic, and the current state, it's so easy to code this state machine already. Okay? It's like in 3 minutes or a minute, if you or let's say 5 minutes, if you can type really fast, you can immediately think about, okay, how can I design this very basic state machine? So the first step is to create the current state registers. So this code over here is pertaining to this current states, right? So you create the current state, and then you can use local parameters or parameters, depending what you use. I prefer that you guys use local param, because it's as if you give it to some other designer, they're gonna think about, okay, this local parameter is fixed for this submodule only. So it's pretty much fine. And then you just write, okay, what are those states? So we have 4 states, so you need 2 bits, right? And then this is our registered set. The current state is our register, right? It's not a cloud. The clouds here means combination logic. This blue box here is a register. So you just make the register. Always FF passage clock, gets reset. On reset, you go to state 0. And then the current state is just a simple update from the next state combinational logic, right? That's the input. So that itself, okay, when you code this thing, you're done. You already have your current state register. Okay, that's it over there. Now the next thing you want to design is the create the logic for the next state. This one, the combinational logic here. Okay, so make the logic for the next state. Wire in some input control because it's mealy. So we have an input that tells me, okay, depending on my current state and my input, I'm gonna decide which state I'd like to go to. Right? So it's a combinational logic. So always come over here, and depending on my current state, let's say I'm current state 0, I have an input 1, my next state is you have to go to state 1. Right? So if you look at here, if my current state is I'm at state 0, it's a case statement. Right? If I'm at state 0, my next state will be dependent on some input control logic. Right? So if it's 1, I'm gonna go to state. Whoa, that's wrong. Sorry, that I messed that up. So this has to go to state 1, right? If it's 1, I go to state 1. If the input is 0, I go to state 2, rather. Okay, over here. And then if you're in state 1, okay, if I'm in state 1, if it's 1, okay, I go back to state 1. You could see it here. And if my input is 0, if my in control is 0, I go to state 2. Okay, so this is correct. And then in state 2, look at it. If I have an input 1, I go back to state 1. Right? But if my input is 0, I go to state 3. That's it. And then in state 3, I don't care where I'm going. I'm just going to go to state 0. So I just go to state 0. Presto. This is your next state combinational logic. And that's easy to do, right? You just have to do a case statement on the current state. And then per current state, you have this. You can do it with an if-else condition, but here I just used a multiplexer instead, a conditional in control since it's just 1 bit, right? Then if I do that, hey, I know which state to go to. It's that simple, right? I mean, it's like pretty much straightforward. And then the output, okay, the last thing you have to make is to create the combination logic for the output, right? And it's so easy. It's also the same thing. Depending on the current state and your input, that's pretty much it, right? If my current state is 0 and I input a 1, right, my output is 0. Bam. If my current state is 0 and I input a 0, my output is 1. Bam, done. In state 1, if I go to state 1, okay, in both cases, whether I'm a 1 or a 0, my output is always 0. So you just say the output is 0. Okay. In state 2, the output, okay, over here is the input dependent. So input and state dependent rather. So if my input is 1, I put a 0, right? And then if my input is 0, I put a 1. That's it. And then for state 3, my output is always 1. I just put a 1. Okay, whoops, I put the double over there, but that's fine. Okay, and that's it. And then all in all, this entire state machine and this mini machine that you made, whoops, you can code it that way. So you can compartmentalize it. So the current state here, the outputs are here, and then the inputs are here. The next state logic is here. Right? It's pretty much the same thing. Okay, so that's a complete set for the finite state machine code. And then you grab that code, put it in your machine, in your submodule, and then done. You already have a finite state machine. So the thing is that knowing how to do this, I expect, or somehow, if my point is that if you can visualize your design, then you can do an HDL code for the microcontroller state machine. And always keep in mind that it's hardware and it's not software. You're trying to describe, you're trying to describe this. Okay? That's the mindset that you need to have. Okay. Okay. All right. So that's how you make it. Unfortunately, you don't have an exercise. Do you want an exercise to make a multi-cycle controller? That would be fun, but I'm thinking about it because that will take time again. Okay, so in summary, we know how to create a state diagram for an NC processor, and you also know how to write it in System Verilog. Okay, so yeah, that's pretty much it. Yeah, that's the end of this discussion. Time check. Okay, oh, fantastic. That is very quick. So I hope you guys understand how to make the finite state machine. And it's a very useful method because when you do go into industry and try to work it out, um, several of your designs will have finite state machines. It won't disappear. It's always there. Okay. And yeah, it's like a very important fundamental that any digital designer must know. Okay. So any questions? No questions? Okay, that ends this discussion. I'm gonna stop the recording.